Hello and welcome to this revision session on paper 1 for AQA A-Level Physics. So the aim of this particular revision session is trying to answer examination questions on the topics found on A-Level Physics paper 1. So if we are successful in learning this particular lesson, we should be able to answer A-Level Physics examination style questions. You should then be able to assess your own understanding on A-Level Physics and then finally understand what topics we need to improve upon for your A-Level Physics qualification. So let's first look at a little bit of preparation for this revision session. When you're completing your work in this revision session, I would recommend that you divide your piece of paper into two sections, making the left hand section larger than the right hand. Now on the left hand side, write down your working out and answers to the questions in this revision session. Now when you're doing this, try and answer your questions in full sentences and show your full working out. Whilst on the right hand side, in this section, write down any piece of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now before we look at some questions, have a look at some tips on how you would answer certain styles of A-level physics questions. So let's firstly consider a mathematical question. Now the first tip I would suggest is you circle or underline the key values given in the question. Now certain values may be used in later parts of questions, but no information in the examination question will be useless. The second thing you need to do is when you're looking at a mathematical style question is look at what you're being asked to calculate. So make sure you're very well aware of what the question is asking you to work out. The next tip would be to then review the equation book which comes along with your examination and then find the appropriate equation to use. Now in many situations you'll need to rearrange this equation to place it into the correct form. Now the next thing you should then do is you look at the information given in the question, ensure that all values are given in correct units with correct prefixes, and you check the units are SI and that there's no clear prefixes which you've missed out. Then what you should do is make sure you're aware of any standard values you would need to know for this particular question. So things such as the speed of light in a vacuum, Planck's constant, the refractive index of air, 1 eV in joules, the number of seconds in an hour, or the number of radians in a circle or one wavelength. Then you will place your values into the equation, but do not round until the end of the question. What you would then do is you would then work it through and underline your final answer in your work, place it with the lowest significant figures found in the question, and give the units with the answer. Now the last thing you should really be doing with a mathematical question is then check the answer is an answer you would expect. So for example, in this particular question we've worked out the speed of light in the glass to be 2.07 times 10 to the 8 meters per second. So it's on the same order of magnitude as the speed of light in a vacuum, but it is smaller, so the answer is most likely to be right. It's very important that when you're doing mathematical style questions you learn to estimate values, and the adage would be if it does not look right it probably is not right. So always do a logic check on any of your answers. Now how about a written question? Well, the first thing you should always do with a written question is look to see if there's any words in italics or in bolded. Now these are either key terms you're expected to remember or key bits of information which will be important later in the question. The second thing to do for a written question is look at the number of marks allocated to the question and always try to make the same number of points as marks given in the question. Now you should always read the question carefully and ensure you answer the question that's asked and not the question you wanted to ask. So you should really make sure your answer is specific to the question that is asked. The advice I would always give is imagine it is a conversation, and if your answer does not directly respond to the question asked, it will be like in a conversation you not answering the question someone asked you verbally. Always ensure you are answering the question that has clearly been asked on by the question. Now the next thing you should then do is review the key action word of the question. Use this to guide how you should answer your question. So for example, if it's explain, you would define or describe a response, for example. Now, tip 5 is answer the question. Now, ensure when you're answering your question, answer in a clear and concise manner. Don't write down any extra information, and don't feel you have to fill all of the space given in an examination booklet. Make your answer relevant rather than long. Now, after you've written your answer, always try to check your answer. So think to yourself, have a little mental checklist when you write your answer. Does it sound vague? Does it clearly answer the question asked? Do you contradict yourself in your response? Have you spelled the key words needed for physics correctly? Would you say you say this answer in a conversation? If it does not sound right, then it probably will not get full marks. So in this particular example, what will we do? We'd have to make sure we learn the definition of coherent, because it's a bold word, so you need to know what that word means. Okay, you would then also as well, linked in the idea, it's a constant or fixed same phase relationship or difference between the two waves. You would then, in the next question, learn how Y fringes form and how an interference pattern is produced. So for example, a single slit acts as a point or single source diffractant spreading light to both slits. And then finally, you would detail the different steps needed to form a bright fringe. So for example, you would notice 3 marks, so we're looking at 3 different points. So it's the idea of superposition of waves from 2 slits, the diffraction patterns from both of the slits overlap and interfere constructively. So at this point, we know that waves from each slit are meeting in phase. Right, now just to clarify back on our examination questions in physics exams, let's look at a sample question here. The tip I would always suggest is always check for units and prefixes found in any question. You then try and convert any prefixes and any units into SI units, and again be aware of equations to work out areas and volumes for different shapes, and watch out for questions given diameter when you need to use the radius. Here, if you've got a graph, it's important that when graphs are given in examinations, please use the graph to help you find the answer. Remember that the trend and the values that you are using are only valid for the data range on the graph. And if the graph is a straight line graph, you've got to use the equation y equals mx plus c to find different quantities on the graph. So for these questions, they'll give you the equation of the line in some form. Now again, if the gradient must be calculated for a straight line, you've got to use the entire straight line section, but in addition you would draw the lines on the graph to show extrapolation of where you worked out your gradient from. But if the gradient is a curve, you would use the tangent to derive the gradient. So again, you've got to really have an understanding of what the gradient and areas represent on each graph that you come across in a physics examination, and be aware of key markers on a graph. So a famous one will be a stress strain graph. Understanding where the limit of elasticity is, understanding where the limit of proportionality is, understanding where the breaking point is, and the ultimate tensile stress. Now in questions with lots of information in physics exams, it's very, very important you read all of the information carefully, as this will provide a basis of your answer. Now the hints of the answer can be given in all of the information, and you're not expected to memorize everything in a physics exam, so you will have some information given to you in the question that is written down in the exam. So, but finally, again, just to clarify, remember to learn your key basic definitions in physics. So for example, stress, strain, coherence, interference, superposition. There are just key fundamental ideas in physics you've just got to memorize. So with that being said, let's have a go at some questions. So the first topic we'll look at is particles and radiation. So here, figure 1 represents the decay of a particle X into particle Y and 2 other particles. The quark structure of particle X and particle Y are shown in the diagram. Deduce the name of particle X, state the type of interaction that occurs in this decay, and state the class of particles to which W- belongs. So at this point, pause the video and then restart the video when you are ready to go through the answers. So, what are the answers to the question? Now the first one, you've got to be aware of what particle is made of quarks of UDD, so that should therefore be the neutron. Now again, state the type of interaction that occurs in this decay. Well, the big hint is either that you're producing leptons, or you've got quarks changing type, or you've got a W- exchange particle. So it has to be the weak interaction. Remember, type of interaction means one of the fundamental forces, not an actual named decay. Now, what class of particles do W minus belong to? Well, you'll notice that they're being exchanged from one particle to another, so these are the bosons or exchange particles. Let's now look at another question. So here, show clearly how charge and baryon number are conserved in this interaction. In reference to all the particles, including quarks, in your answer, name the only stable baryon, and a muon is an unstable particle. State the names of the particles that are produced when a muon decays. So once again, pause the video and only restart the video when you've answered the question. Right, so let's go through the answers. So you're going to have to show conservation of charge and baryon number. So a few things to note here. Firstly, you're going to have to use the equation booklet to find the charges of the different quarks and the baryon numbers of the quarks. You then got to set them all out, showing what it is before and what it is after. Now again, the other hint is it's got to refer to all the particles. So even if you don't have a value for charge for the neutrino, you've still got to include it, and even if you have a no value for baryon number for the neutrino or for the electron, you've still got to include it because it says refer to all particles. The next one is a fact. What's the only stable baryon? It is the proton. That's a fact you've got to know. Now, a muon is an unstable particle. State the names of particles that are produced when a muon decays. Again, it's very important to note that this most stable lepton is the electron, but when you have an electron being produced, you will always produce the electron antineutrino, and because you've got your muon decaying, you will produce a muon neutrino as well. So let's have a look at the next question. More than 200 subatomic particles have been discovered so far. However, most are not fundamental and are composed of other particles, including quarks. It has been shown that a proton can be made to change into a neutron, that protons and neutrons are made from quarks. Now, name one process in which a proton changes into a neutron, name the particle interaction involved in this process, and write down an equation for the process stated in 3.1 showing that the baryon number and lepton number are conserved in this process. So pause the video now, answer the question, and then resume the video. Right, so the process that can change a proton to a neutron are either an electron capture or a beta plus decay. Now, in both instances, because we are having quarks changing type or flavor, it must be the weak interaction. Now, you then got to once again show that baryon number and lepton number are conserved. Again, show the values beforehand, show the values afterwards, and they've got to equal each other. And remember, you show the values for baryon number and lepton number for all the individual constituents in the decay process. So, the next question. The strange quark was used to explain the existence of particles whose tracks had been seen in experiments in the early 1950s. These were unexplained at the time and were referred to as strange particles. One of these particles was later named the K plus kaon. State the quark composition of a K plus kaon, and a K plus kaon decays into a pi plus particle and a pi zero particle. Explain one property which is conserved and one property which is not conserved in this decay. So pause the video now and then resume the video when you've answered the question. Right, so what's the answers here? Well, the first thing you've got to be able to do is look at the back and understand that it's going to be a meson. So you're going to have one quark, one antiquark. Now, because it's a kaon, it must either contain a strange or an anti-strange, because that is the definition of a kaon. And therefore, the two particles, the quark and antiquark, must then add up to give a charge of +1, because it tells you it's a K+. So the two that do this are the up and the anti-strange. Now, once again, you can refer to the charge and baryon number and strangeness by looking in the back of the equation book. The next question here. The first thing which should be conserved is anything in a particle decay. That would include momentum, energy mass, baryon number, lepton number. Now, the one thing which is not conserved, which links into kaons and the strange particle, is strangeness, because we know that for these types of particles you don't have to conserve strangeness, and it can change by 1 in your decay process. Right, let's look at the next question to do with particles. Monochromatic light is shone onto the surface of a clean metal plate. The photoelectric effect results in electrons being emitted from the surface. State and explain the effect on the emitted electrons if the frequency of light is increased, the intensity of light is increased, and explain how the photoelectric effect supports the particle model of light and not the wave model of light. So, pause the video now, answer the question, and resume the video afterwards. Right, so what happens to the emitted electrons if the frequency of light is increased? Well, the electrons will be moving faster. They would have a higher kinetic energy. That's because if you increase the frequency of the light source, this increases the energy of the photon, so that will then leave more energy for the emitted photoelectron. Now, what would happen if the intensity of light increases? Well, the effect will be that the number of electrons emitted increases. This is because if the intensity of light increases, there are more photons being absorbed every second by the metal surface, so there are more photoelectrons being released every single second. Now, explain how the photoelectric effect supports the particle model of light and not the wave model. Well, the first thing is that the number of electrons emitted depends on intensity and it doesn't depend on frequency. The emission of electrons is instantaneous and there's no time delay, that there's a minimum frequency for electron emission, and that also the electron energy depends on the frequency, not the intensity of the photons. Now, why is this? Because if it is a particle model of light, the particle model of light indicates that each light particle or photon has an energy equal to hf. So then one photon would release one electron, which is a very important idea in the photoelectric effect. So the electron release requires a minimum energy or a work function, and this electron energy is therefore going to be the photon energy minus the work function energy to release that electron in the first place. Now, if it was a wave, in this instance, if light was acting as a wave, well, wave energy depends on intensity. So the energy is spread over the whole wave. And the energy supply would be continuous and the energy would build up over time. So it would mean that the electrons would be emitted after a certain time delay. So, in theory, you would say that if light was acting like a wave, more intense light should give a greater kinetic energy for the emitted electrons, and it doesn't. Or if given enough time, electrons would always eventually be released from the metal. They don't. Only certain situations are photoelectrons released. And finally, there'd always be a delay between the light being shined on the metal and the electrons being released. That is never observed. Emission always happens instantaneously. Right, let's look at another question now. The threshold frequency of lithium is 5.5 times 10 to the 14 Hz. Calculate the work function of lithium stating an appropriate unit. Calculate the maximum kinetic energy of the emitted electrons when light of frequency 6.2 times 10 to the 14 Hz is incident on the surface of a sample of lithium. So pause the video now and answer the question. Right, so you've got to use your work function equation here, where we know that the work function is equal to hf because it's going to be equal to E equals hf, where f, though, in this case is going to be the threshold frequency. So you'd work it through like that. Remember your value for Planck's constant to get 3.65 times 10 to the 19 joules. Now, in this case, what's our maximum kinetic energy? Well, it's going to be this photon energy, which you've just worked out here. Then you minus the work function, so it'll be 6.63 times 10 to the minus 34, Planck's constant, times by 6.2 times 10 to the 14, which, if you notice from the question, is the frequency of the radiation. You then subtract your work function to get 4.6 times 10 to the minus 20 joules. Let's have a look at another question. So this graph shows the results for an experiment to demonstrate the photoelectric effect by illuminating a clean metal sheet with light of increasing frequency. So state a quantity and its unit, which could be plotted on the y-axis for this graph, and then explain why there is a threshold frequency. So once again, let's pause our video now, and what's our answer going to be? So the first thing is state a quantity and its unit. Well, it's going to be maximum kinetic energy, which will have a unit of joules or electron volts, or you could have stopping potential with the volts as well. Now the threshold frequency is shown on the graph. So what's going on here? Well, it's the idea that one photon is absorbed by one electron at a time. That's a fundamental principle of the photoelectric effect, that one electron trapped in the metal can only absorb one photon at a time. Now this photon energy is given by E equals hf. So this tells us there's a minimum energy needed for the emission of the electron, which is given by the idea of the work function. So the emission of electrons only occurs if the frequency of light is greater than the threshold frequency, if the photon energy is greater than the work function. So let's have a look at another question. So the discovery of the Higgs particle was an important contribution to our understanding of particle physics. Describe the standard model of subatomic particles, and you should identify the fundamental particles and the composition of the particles we can observe. So what do we know? Let's pause the video now. Right, let's have a look at how to answer this question. So let's consider what the standard model for subatomic particles are. So what are your fundamental particles? You should know that things are made from either quarks or leptons. Now there are two types of particles made from quarks. You've got your baryon made from 3 quarks, and you've got your meson made from 1 quark, 1 antiquark. Now this leads to the idea that there are in fact 6 quarks: up, down, top, bottom, charmed and strange. Now there are also 6 leptons. So you've got your electron, your muon and your tau, and then you've also got your associated neutrinos with them as well. Now, and finally, you should also note that for every particle there is also an antiparticle as well. Let's now have a look at another question. So describe the interaction that's responsible for keeping protons and neutrons together in a stable nucleus. You should include the details of the properties of the interaction in your answer. Now, nuclei can decay by alpha and beta decay. In alpha decay, only one particle is emitted, but in beta decay, there are 2 particles emitted. Explain how baryon number is conserved in alpha and beta decay. So pause the video now, answer the question, and resume the video when you've answered the question. Right, so the first thing we're going to think about is what's the force keeping protons and neutrons together, and discuss what this interaction is. So the first thing you need to remember is it's got to be the strong interaction, which is very short range, less than 5 femtometers. Now it's an attractive force up to 5 femtometers, but it's a repulsive force less than 1 femtometer, and it doesn't really exist. It's negligible beyond 5 femtometers. Now it only affects hadrons, which are things made from quarks, so it will affect your protons and your neutrons, and the mediator, the exchange particle of the strong interaction, is going to be the gluon or the pion, which is the same particle with just 2 different names. Now the next question, we're going to have to think about how the baryon number is conserved in alpha decay and beta decay. So let's think about alpha decay. Well, the baryon number is going to be conserved because the number of protons and neutrons in total is unchanged. In alpha decay, your alpha particle is released from the nucleus, but the overall number of nucleons remains unchanged, and the type of nucleon remains unchanged as well. So therefore, the baryon number will always be the same. Now in beta decay, a neutron turns into a proton. Now that's okay because they both have the same baryon number, 1, so as a result it won't change the baryon number. And then the final thing you've got to talk about, because remember the question said there are 2 particles produced in beta decay, is that you will also have a beta particle and an antineutrino produced. Now both of these have a 0 baryon number, so it'll ensure the baryon number is conserved. The next question, kaons are mesons that are produced by the strong interaction between pions and protons. The equation shows a reaction which a kaon and a lambda particle are produced. Deduce the quark structure of this particular particle. The kaon decays by a weak interaction, and the equation shows an example of kaon decay. State one feature of the decay which shows us an example of the weak interaction. And finally, there's been considerable advances in our understanding of particle physics over the past 100 years. Explain why it's necessary for many teams of scientists and engineers to collaborate in order for these advances to be made. So once again, pause the video now, answer the question and resume the video afterwards. So the first thing we've got to note is we've got to look at what's before and what's afterwards, and then see if we can work out what the structure is going to be. Now the first thing to note is we know what the quark structure of a pi minus is going to be, because it's a particle, it's a meson, so it's a quarked antiquark, so you can work out the combination of the two to give a charge of minus without using a strange particle, and the quark, I should say, not particle. And then you should know the proton off by heart is up, up, down. So therefore what you can then say is you can then start to work out what must be conserved. So the first thing to note is if the pion is a meson, so it's a barrier number of 0, and the proton has a barrier number of 1, and we know the kaon is a meson, well, that tells us that this particle, this lambda particle, must be a baryon to conserve the baryon number, so it must be made of 3 quarks. The next thing to note is that because the strangeness beforehand is going to be a 0 value, and the kaon is producing a strangeness of +1, well, this particular lambda particle has to have a strangeness of -1 to cancel it through. Now we know the strangeness has to conserve because it's via the strong interaction, and strangeness is always conserved in the strong interaction. So therefore we now know that one of our quarks must be the strange quark. And now we've got to understand that we need to have 2 further quarks, not antiquarks, which then add up with the strange to then give us a charge of 0. We know it's a charge of 0 because it gives us a 0 value in our symbol. So that is up, down, strange. Now, next question, one feature of this decay, which is an example of the weak interaction, well, it's the strangeness isn't conserved. That's a fundamental idea, especially when dealing with kaons. Now, the last one is a very much a response you've got to memorize. The idea that results from experiments can be independently checked or validated, which we would call peer review. Particle accelerators are very expensive, and collaboration helps spread the cost of building them, and there's many skills and disciplines are required, which one team would like you to have, so it's important we all work together. Let's now have a look at some questions on mechanics and materials. So let's have a look at the following question. A physics class made a toy rocket. A drinks bottle was partially filled with water and inverted over a valve. The air pump delivered air to the bottle until pressure forced the bottle from the valve, and the water was ejected from the bottle at a high speed. You can now see a velocity time graph for the first 4 seconds after takeoff, determine the height to which the rocket travelled. So again, pause the video now and resume the video once you've answered the question. Right, so what can we do? Well, we've got to understand that we've got a velocity time graph in front of us. So with a velocity time graph, we know we can work out the distance travelled, or the height it will go to, by using the area under your particular graph. So you'd have to attempt to find the area. So what you would do is, you can see here we've got a triangle-like shape. So we can do our area by doing a half base times by height. So it's a half times by 1.9 times by 20. So there you can see straight away your answer is going to be 19 meters. Always remember, you should know what the gradient and what the area underlines are in every graph given to you in a physics exam. Next question. Solid carbon dioxide changes state directly from solid to gas. This process is called sublimation. Solid carbon dioxide, when placed on water, will move rapidly across the surface due to jets of ejected gas. The diagram below shows the direction of movement for 2 large pieces of solid carbon dioxide placed on water. When placed at rest on the water, piece X begins to move rapidly in the direction shown. With reference to Newton's laws of motion, not momentum, explain the motion of piece X. So, pause the video now and resume the video when you've answered the question. Right. So, the first idea would be that the solid carbon dioxide exerts a force on the gas. So, therefore, from Newton's laws of motion, because there are 2 objects, it means we've really got to focus on Newton's third law. So, this means the gas will exert a force back on the solid, and now the force will in the opposite direction be of the same size. So, what this now means is that both the gas and the solid have a resultant force acting on each of them. So, therefore, from Newton's first law, we know that the acceleration is going to take place for both, because if both have a resultant force acting on them, they will both accelerate. Now finally, you would notice that from Newton's second law, F equals ma, so A equals F over m. Because m is very small, it tells our acceleration is going to be very large. It's very important you know and can describe all three of Newton's laws of motion. Let's have a look at a new question now. So the shot put is an Olympic field event. The distance for the women's world record shot put is in excess of 22 meters. The shot is a metal ball which is thrown from a standard position so it lands on the ground a horizontal distance r from the thrower. A shot is thrown from a height h above the ground with an initial velocity of 14.2 meters per second at an angle of 37 degrees to the horizontal. The time it takes for the shot to reach the ground is 1.98 seconds. So that the vertical component of the initial velocity is about 8.6 meters per second, and calculate the height h above the ground from which the shot was thrown. So pause the video now, answer the question, and resume the video when you have answered the question. Right, so how do you work out a vertical component? Well, you would draw your triangle in and look to find your horizontal and vertical components from the triangle you would draw, and you can hopefully see straight away that from the angle you've been given, to work out the vertical from drawing the right angle triangle is going to be v cos theta, so it's going to be 14.2 cos 53 degrees, so you can therefore see it's going to be 8.55. You could also say it's 14.2 sine 37, because that's the same value. That will also give you 8.5. Now, calculate the height above the ground from which the shot was thrown. Now, this needs us to use our equations of motion. Now, it's very important you memorize your equations of motion and how to use them. So we look and see what have we been given. Well, we now know what the initial velocity is going to be, 8.55 meters per second. We know that we know what the time is, because I believe we are told in the question it is 1.98 seconds. We also know what our acceleration is going to be, because it's coming down, so it's going to be 9.81 due to gravity, and therefore we can use the equation s equals ut plus a half at squared, and from that we can work out s. So our answer is going to be minus 2.3 meters, which if we use minus as going down like that, that indicates it's above the ground. Right, so the next one is now calculate the horizontal distance r for this throw. So once again, pause the video now and then unpause the video when you're ready to go through the answer. Right, so how do you work this one out? Well, we know what the horizontal component of the velocity is going to be. It's therefore going to be 14.2 cos 37 degrees, or 14.2 sine 53 degrees, times by the time now to then give you your value for r, because we know that velocity is distance over time, so therefore distance is going to be velocity times time, so therefore we times by 1.98 because the time is a constant value between horizontal and vertical, so it gets to 22.5 meters. Now you might think, how can we use this equation? Well, we only use our equations of motion in the previous one because we had a constant acceleration. In the horizontal, you'll notice in this case there's no force acting on it, so it has inertia, and when an object has inertia we can just use the equation velocity is distance over time. Right, let's have a look at another question. Figure 1 shows a truck moving freely down a ramp inclined at an angle to the horizontal. The truck starts from rest at the top of the ramp and reaches point A. Friction and air resistance are negligible. As the truck moves down the ramp to point A, its centre of mass has a total vertical displacement of 8.0 meters. Calculate the speed of the truck at point A. So pause the video now and then unpause the video when you've answered the question. Right, so the first thing I think about is upper height and now it's moving. So I tend to do this by doing the conservation of energy. I would say that EK is equal to EP. So I'll say half mv squared equals mgh. First thing I then do, cancel through the m's, so it's a half v squared is equal to g times by h. I then pop in the values, make v the subject, and I get an answer of 12.5 or 13 meters per second. I mean, the other way you could do it is by using the equation v squared equals u squared plus 2as, by using your equations of motion. That will also get you your answer rounded to 13. Let's have a look at another question then. So figure 2 now shows the truck moving down a ramp with a varying slope. The truck starts from rest and moves freely down the ramp. It reaches point C and then moves along the horizontal runway to D. Friction and air resistance are negligible. Discuss how the acceleration of the truck in figure 2 differs from the acceleration of the truck in figure 1. So again, pause the video now and then only unpause when you've answered the question. Right. So, what's happening here? How does the truck in figure 2 differ from the acceleration you just saw previously? Well, the truck in figure 1 is going to have a constant acceleration because the gradient of the ramp that's going down is constant. So we always got to talk about that. But now let's talk about figure 2. Think about its curving and sloping downwards. So in figure 2, the acceleration is greatest at the top because the slope is the steepest. The acceleration then decreases, and then between C and D, the acceleration will be 0, or you'll have uniform velocity, because we now know that we're on a flat surface, so the component of the weight is now parallel to the slope change. So again, make sure you talk about all those key points in your answer. So now let's have a look at the topic of electricity. So have a go at answering the following question. The resistance of the filament lamp at its working temperature is 14 ohms. The filament has a length of 0.36 meters and a diameter of 32 micrometers. Calculate the resistivity of the metal that's used for the filament when the lamp is at its working temperature. Give an appropriate unit for your answer. Pause the video now and unpause the video when you want to go through the answer. Right, so the first thing I'm thinking about is its resistivity, because we then need to put the equation in. Rho equals RA over L. We need to convert the values into SI units, so micrometers needs to turn into meters, and we also need to calculate A from the diameter. So the first thing you need to do is you need to calculate A from the diameter, which is pi over D squared times by 4. So you can then work it through like that, making sure you have your diameter in meters. You get your correct resistivity by doing rho equals RA over L, and you're given R in the question and you're given L. You can then write out to be 3.18 times 10 to the minus 8, which is appropriate for a conductor, and then the units of resistivity are something you shouldn't be memorizing: ohm meters. Let's have a look at the next question. A meter bridge is a circuit which can be used to measure an unknown resistance accurately. The meter bridge includes a meter length of nichrome wire. Calculate the resistance of the 1 meter length of nichrome wire. Once again, pause the video now and unpause the video when you want to answer the question. Right, so again, the first thing you would do is rearrange your resistivity equation to make resistance the subject. So R equals rho L over A. We now know it's a wire, so we know our area is pi R squared. So you can therefore work out the area to be pi D squared over 4. So therefore you can use that to then work out your area correctly, pop it into your equation and work it through like that to get a resistance of 8.9 ohms. Next question. The meter length of wire labelled AB is connected to a 1.50 volt cell of negligible internal resistance and switch is shown. Explain how the potential along this wire varies with distance from A when the switch is closed, and show up that the potential difference between A and the 0.75 centimeters along from the wire from A is about 1.1 volts. So once again, pause the video now and then resume the video when you've unpaused. Right, so first thing we can say about B.1 is you've got to know that resistance increases with the length of the wire, because the longer the wire, the more ion charge carrier collisions, the greater the resistance. And we know that potential difference is proportional to resistance, so potential difference is proportional to the length of the wire. Potential difference is proportional to resistance because the greater the resistance, the more energy per charge needed to push the charge through the wire to maintain the same rate of flow current. So that's where it comes from. Now, the next one, part 2, what you would do is it's a ratio of length is equal to a ratio of potentials, because we know that they are directly proportional to each other. So we'd say 75 over 100 times by 1.5 is equal to the potential of P. So it's going to be 1.13 volts or 1.125 volts. Let's have a look at the next question. Figure 2 shows the current voltage characteristics for a resistor in a filament lamp. Explain in terms of electron motion why the IV characteristics for the filament lamp is a curve. 4 marks. Pause the video now and unpause the video when you want to go through the answers. Right, so we need to think of some 4 or 5 clear points we would like to make on this. So first thing is an increase in current or voltage leads to an increase in temperature in your lamp. So it increases the movement of the ions or lattice or the metal atoms in your filament lamp. Now this means that the amplitude has increased. So this means that it increases in the rate of collisions with the charge carriers, with the electrons. So the resistance increases as shown by the fact that the line is now a curve. Next question. The meter bridge is shown here. The circuit includes a resistor of resistance 3.30 ohms, a very sensitive ammeter, and a resistor of unknown resistance R. A metal slider can be moved along the nichrome wire and pressed firmly against it to make an electrical connection. When the switch is closed and S is 75 centimeters along the nichrome wire, the ammeter reads 0 amps because the potential difference across the ammeter is 0. Calculate R. So pause the video now and unpause the video when you want to go through the answers. So how can you do this? Well, the first way I would do it is by doing the current, by saying the current is I equals V over R. So therefore it's going to be 1.125 because that's what we know V is going to be in R. Then divided by 3.30 and then we can work it out to be 0.34 amps. Now it's therefore important to note that that can then determine what our value of I is throughout the circuit. So how can we then work out R? Well, we know R is equal to V over I. So we know that in the resistor that we don't know about, that V is equal to 0.375. We know that because we can look at the ratios of the two. So if the total is 1.5 volts and one takes 1.125, the other's got to take 0.375 because the two added together give you the 1.5 volts. Or you could do it by doing the ratios of the length. So you say 0.25 over 1 times by 1.5 is equal to 0.375 as well. Then you know what V is, you know what I is, it's 0.34, because if you notice the two resistors are in series with each other. So if they're in series, the current is the same in both of them because current is constant in a series circuit. So therefore our answer is 1.1 ohms. You can also do it another way, by the way. You can also ratio the two potential differences. So what you can say is if you know the potential difference of each one, which you can do by your ratio, so you know that one is at 25 and one's at 75 because it links into the lengths. We can say 25 over 75 is the ratio of the two lengths, links to the two resistance potential differences, and therefore they're the ratio of the two resistors. So you can then work it through like that as well. Right, let's have a look at another question. Figure 7 shows a cylinder of conducting putty which is 60 millimeters long and 20 millimeters in diameter. The conducting putty obeys Ohm's law. State Ohm's law. Then a 1.5 volt DC supply of negligible internal resistance is connected across the ends of X and Y of the cylinder of the putty. The resistance of the cylinder of the putty is 20 ohms. Calculate in milliamps the current in the putty. Again, pause the video now, answer the question, and when you've unpaused the video, we'll go through the answers. So you've got to memorize what Ohm's law is, and that is the current through a conductor between 2 points is directly proportional to the potential difference across those 2 points when the temperature is constant. That's a fact you've just got to learn. Now in the next one, what do we know? We know that R is equal to V over I. So you can then, you got V in the question, okay, you've got R, so you can work out what I is. Now the other trick to note is if you have your resistance in ohms, you have your potential difference in V, that will therefore give you an answer in amps. You then got to convert it into milliamps by times in your answer by 1,000, because we're going from a bigger unit into a smaller unit, so we multiply our answer by the change in the number of zeros that we need to include in there. So we're changing by 1,000, so we multiply by 1,000 or 10 to the 3. Next one, a student suggests an arrangement for demonstrating that the putty obeys Ohm's law. Discuss any problems that the circuit and components shown in figure 8 might make this unsuitable for the purpose. So again, pause the video now and unpause the video when you want to go through the answer. Right, so let's have a look at a few things here. The voltmeter is going to be an issue because we'll look at that in a second. And then also, okay, we need to look at the value of resistance. Now, again, this stands out to me because they've literally labeled the value of the resistance of the rheostat. So it's going to be important. If they highlight such a fact and signpost it, that's what they want you to look at. So the answer is, firstly, the voltmeter is in the incorrect position because it's across the cell. Well, we want to show it's the putty that's demonstrating Ohm's law. So the voltmeter should be measuring the putty. So it should be connected across the putty. The next thing is, you'll notice that the potential difference of the cell is 1.5 volts, but the resistance of the rheostat is 10 ohms. So this tells us that it's not suitable enough to control the current because the resistance is only half that of the putty. So it would only have quite a short range of potential differences. So we'll go from about 1 volt to 1.5 volt. So you wouldn't get a very good relationship because we don't know if it's true or not for a big enough range of values. Next question. A student is taking measurements in order to determine the resistance of a component in a circuit. He connects a voltmeter in parallel with the component and an ammeter in series with the component. Explain why the voltmeter should have a very high resistance. Pause the video now and then unpause the video when you want to go through the answer to the question. Right, so why should a voltmeter have a very high resistance? Well, it's important to note that we want very little current to flow through the voltmeter. Otherwise, okay, what would happen is that it would mean that current passes through the voltmeter and that would then change your actual resistance. So if you have a very high resistance in your voltmeter, that means that there's going to be very little change flowing through the ammeter in the circuit, which means that the ammeter is reading the right value. Because if the voltmeter had a low value of resistance, it would change the current flowing through the ammeter, which would then change the actual value in the circuit, which is what you don't want. The other way you can think about it is that a voltmeter is connected in parallel. So because we know that we can work out the resistance in parallel by doing 1 over R1 plus 1 over R2 equals 1 over R total, a very high value will give a very small difference because we're doing 1 over. So you want a very high value of resistance so the total parallel combination of the voltmeter and the component isn't changed that much by the addition of the voltmeter. Right, let's have a look at another question. A practical demonstration of this principle uses two rectangular electrodes opposite each other on either side of a pipe, a distance of 0.60 millimeters apart. The dimensions of the electrode are shown in the diagram. The electrodes were connected to a 1.5 volt cell. Salt water was pumped through using a magnetic field of magnetic flux density 0.40 teslas. Show that the current through the salt water is about 20 milliamps, with the resistivity of the salt water being 1.6 ohm meters. Once again, pause the video now and unpause the video when you want to go through the answer. So, first thing that it shows me is we've been given the resistivity, so we need to use the resistivity equation, but we need to work out current. Now you tend to work out current from the equation V equals IR, so I equals V over R, so we need to use the resistivity equation to work out resistance. So first thing is we rearrange our resistivity equation to give us our resistance. So we can get the resistivity equation for the examination book, so rho equals RA over L, so R equals rho L over A. We can then work out A, it's rectangular, so it's quite an easy one now to work out its area, so it's going to be 0.5, which is the height, times by 28, which is the width or the length. Now we're going to do times 10 to the minus 6 because both of them are in millimeters, so it'll be 0.5 times 10 to the minus 3 times by 28 times 10 to the minus 3, which then links to just 10 to the minus 6 in total. Therefore that gives us an R value of 68.6. We can then use V equals IR, so I equals V over R, so it's 1.5 over 68.6, which gets us 0.022 amps. But the last thing is we want to be in milliamps, so we're then going to multiply it by 1000 because we're going from the bigger unit amps to the smaller unit milliamps, so it gets 22 milliamps. Let's look at the next question. Sketch a graph to show how the current varies with potential difference for a filament lamp. Then the temperature of a filament lamp increases as the current through it increases. Explain this in terms of the structure of a metal. So pause the video now and then unpause the video when you want to go through the answer. So, first thing is you've just got to know what the current potential difference graph is for a filament bulb. And you can see here it's an S shape, but you've also got to remember to draw on both the positive and the negative parts of the curve. Next bit, the temperature of a filament increases as the current through it increases. Explain this in terms of the structure of the metal. Well, this idea of that there's more collisions of the electron with the lattice ions because the lattice ion vibrations have increased because they are now with a higher temperature oscillating with a greater amplitude, so now more energy is dissipated as heat in the lattice, so the electrons will slow down. Next question. A student connects 4 lamps A, B, C and D in the circuit shown here. The battery has an EMF of 9 volts and a negligible internal resistance. Table 1 shows the operating conditions for the lamp when they're at normal brightness. The student observes that 2 of the lamps are at normal brightness and assumes that any changes in the resistance of the lamp are negligible. Determine which 2 are at their normal brightness and use calculations to support your answer. So once again, pause the video now and unpause the video when you want to go through your answer. So, what do we know about here? Well, we need to work out the resistances of each lamp and then use this to then work out what our potential difference is going to be. So the first thing is work out our resistance of lamp B and lamp D. Now we hopefully know that if you look at the information given to us in the question, we've got the operating voltage V and we've got the power, which is in watts here. So what can we then say? So therefore we can say that we know power is equal to V squared over R. So therefore R is going to be V squared over P. So therefore we can take our values for V, square them and divide them by the resistance, the power given in the tables. So you can work out B and D by that, by working out be 3 ohms, and A and C is going to be 6 ohms. So now we know the potential difference across B and D is going to take the proportion of 3 out of 9 times by the 9 volts. Now why do we know that? Well, we know that V is directly proportional to R, we talked about previously in the video. So if one of them has 3 out of the 9, that's going to take 3 ninths of the total EMF, which is actually 9 as well. So it's 3 over 9 times by 9, which is 3. And therefore the resistance of A and C is 6 ohms. So the voltage is going to take is 6 over 9 because it's taken 6/9 of the overall resistance, so therefore it's going to take 6/9 of the overall voltage times by the voltage, which is 9, so it's going to be 6 volts. So this tells us that A and C are at their normal brightness. Right, let's have a look at another question. The student connects another lamp E in the circuit as shown in figure 7. Lamp E is identical to A and C. Explain what the student will observe regarding the brightness of the lamps and refer to potential differences across lamp E in your answer. So once again, pause the video now and then unpause the video when you want to go through the answer. Right, so what do we now know? Well, we need to know the PD across the new lamp. Now it's important to note that lamp E is identical. So we should hopefully know that the potential difference across A to C is going to be 0 because they've got the same potential difference, and the same for B and D, they've got the same potential difference. Or you could argue that the entire strand is got the same potential difference. The top bit's got 9, the bottom bit's got 9, because in a parallel circuit each strand or each branch has the same potential. So this tells us that the potential difference that E is straddling across is 0, so therefore E is not going to light because there's no potential difference. The top strand's at 9 and the bottom strand's at 9. So therefore, if there's no potential difference, there's going to be no current. So therefore, the other lamps are not affected because nothing's going through that lamp E. Remember that you can only get a current if there's a potential difference, and if both branches have the same potential, there's no potential difference. Right, let's have a look at a few questions on periodic motion. So, let's have a look at this question. The United States Space Agency, NASA, uses a centrifuge to test whether equipment will operate when experiencing large forces. The equipment to be tested is attached to the end of the frame of the centrifuge, which rotates around a vertical axis at its center. The centrifuge rotates at 50 revolutions per minute with a radius of 8.8 meters. Show the angular velocity of the centrifuge is about 5 radians per second, and explain how the centrifuge applies large forces to the equipment under test. So pause the video now and then unpause the video when you want to go through the answer. Right, so first thing we need to do is work out angular velocity. So you need to remember that when we're working out angular velocity in radians per second, the change in angle needs to be in radians. So it tells us that there's 50 revolutions per minute. Well, one revolution is 2 pi radians. So that tells us that we're doing 100 pi radians in the minute. However, we're not going to be working in per minute because we're working in per second. So we then need to divide that by 60 to then get us our change in radians per second. And then we should hopefully know that angular velocity is therefore going to be 5.24 radians per second. Now, explain how the centrifuge applies large forces to the equipment under test while we're rotating around. So it's the idea of a centripetal force because we've got rotation going on. Now, it's the idea of you can use your equation of centripetal force to be either mv squared over r or mr omega squared. Now, it's the idea that r is very large and that there's a high linear velocity, so therefore you're going to get a large centripetal force. Let's have a look at another question here. So, the Starflyer is a fairground ride which operates 60 meters above the ground. As it begins to spin, the chairs in which the riders sit in move outwards. Now, consider the chair and the rider as a single object. Now, by drawing a free body diagram and considering the forces acting, explain the following observations. The angle to the vertical of the supporting ropes depends on the speed of rotation, but not on the mass of the rider. So that's worth 5 marks. So once again, pause the video now and unpause the video when you want to go through the answers. Right, so the first thing you really need to do is you need to draw the free body diagram. Now the question is basically telling you that we need to have an equation which has the angle to the vertical in, which shows that v, the speed of rotation, is in there, but that the mass of the rider is not in there. So let's see if we can do that. So the first thing you do is you draw a free body diagram. So in the free body diagram, you're going to have tension acting at an angle upwards and you've got weight acting vertically downwards. So what we can then say is you've got your angle it's working at. Now, out of the 2 examples shown on the screen, I prefer the one on the right because it's easier to understand. But what you can therefore say is therefore if you then want to resolve the 2 forces, you can't say T is equal to mg. Because it's not, it's the vertical component of t which is equal to mg. So when you do your triangle, you'll notice that the vertical component of t is cos, it links to cos theta. So the vertical component of t is t cos theta. So we can therefore say, resolving vertically, t cos theta equals mg. But that's not much use to us because it doesn't have an equation for v in there. Now, what will have v in its equation? Well, in the horizontal, it's rotating in a circle, so it must have a centripetal force acting on it, mv squared over r. Now, that's therefore equal to the horizontal component of t, because there's a horizontal component of t acting towards the center of the circle. So we can therefore say t sine theta in this case is equal to mv squared over r, or mr omega squared. I personally prefer mv squared over r. But the question wanted us to show that m wasn't in the equation for the angle, but v was. So you've got 2 equations now. T cos theta equals mg and t sine theta equals mv squared over r. Now if you do the equation sine theta over cos theta equals tan theta, we can therefore do the horizontal equation divided by the vertical equation and get an equation of the following. We get tan theta is equal to v squared over rg. That works because the m's in the 2 equations cancel through, the t's in the 2 equations cancel through, and sine divided by cos is equal to tan theta. So therefore, we've worked out that tan theta equals v squared over rg. So we've now proven that the equation has, for the angle, includes a term for v, the speed, but not a term of m, the mass. So that finishes the revision session on physics paper 1. So hopefully, if we've been successful and learnt in today's revision session, we can answer A-level physics examination style questions. You can assess your understanding on A-level physics and then understand what topics you need to improve upon for A-level physics for paper 1. So I hope you've enjoyed this revision session on paper 1 for AQA A-Level Physics. Thank you very much for watching and have a lovely day.